Ty was like, moment of panic there. They could almost see me.
Almost.
Oh, that was close, man. That was, whew. Yeah. It's funny how if I ever teach an online class like this, um, I might have like some rule about you have to have your camera on. Like, so like it sucks to just watch a bunch of black screens. It's all about me and what I want. So, priorities.
It's mostly because I got a bunch of dogs and stuff that run around and stuff like that.
Super distracting. And yeah, I mean, you
Yeah.
definitely you definitely have to have yourself muted, like because you never know what's going to happen in the background. And so that's all. It's all good. It's all good. Let's see here. We got to wait a couple more minutes. Wait for everybody to get in. I kind of started at the last minute. Working on summarizing the survey results. I'm going to make a little like Q&A, answer some of the questions that were posed there. Get back to everybody about that. Kind of show some of those results. I thought I would start today, automatically recording, that's good, and go over the email that you should have gotten. I know we've been talking about grading and grades, and I knew there was something coming. So I thought we could just take a couple minutes and talk about that, see if you had any questions about it. I know, like, if you can read this email well, then you know as much as I do. But I thought it'd be worth us going over it together. So there's two basic things that are relevant to you. One is, and I don't think the first one is relevant to anybody here, but you can withdraw all the way up to the last day of the semester. So all the way up to Wednesday, May 13th, you can withdraw. I do know it says somewhere in here that they're working on refunds that they might, maybe it's a different email. They're working on maybe an updated refund policy too, because obviously normally you don't get any refund at this point, but they're working on that too. So hopefully that's not an issue. Nobody's thinking about that for Calc 3. Like, I think we're all going to be okay. But that's something to keep in mind. But more relevant to you is a grading choice that you're going to have, this no harm grading policy. What this means is it's not relevant to me. I'm just going to do my grading, get my grades, submit my grades, A, B, C, D, F, like I normally would, right? So I'm just going to submit those. The option you might have, and it's hard with math courses because often you're in them so you can take another class, but you can have this option in all of your classes after you get your grades, all the way up until June 4th, to decide, you know what, I had an A at midterm and then everything went sour and I ended up with a CE. I don't want that affecting my GPA. So I'm just going to call it a credit received. And you can decide that after you get your letter grade, whether you want it to just count for credit or if you want it to count for a letter grade. And the same thing, it says down further, so D's, you can decide, do you want to count that as the grade? Or do you just want to count that as a no credit, then it doesn't count for your GPA? And there will be no Fs. There are no Fs. Everything that I enter in as an F will automatically get converted to just no credit. So it doesn't harm anyone's GPA this semester. The thing that you have to be careful with about changing it to credit is like, well, I did have an A and I'm going to get a C. If I change it to credit, it doesn't affect my GPA. But your institution you're transferring to, will they take that? Will they allow it if there's a class that has Calc 3 prerequisites? It's complicated for math classes especially. So you can't make that choice unless you talk to an advisor. You have to speak with an academic advisor. So if you're thinking about that, even if you were already getting a C, you're like, well, I'm still going to get a C, but it would be nice to have that C not affect my GPA. Like, then that's totally for you then, but you just have to do some research. Where you're going to transfer to, is that okay for them? If we were a university, we could decide whatever we wanted. We're just going to decide all things, like we could just decide, but we are not. We kind of let some of you go off to other places and we don't know what they're going to do. So this is not something you have to decide now. You will have a couple weeks after grades are turned in. I think 3 weeks for you to decide. If you just leave things, you'll just get the letter grade, and the letter grade is what it is. But you could convert those letter grades to credit, no credit, ABC credit, D and F no credit. You can convert those after the semester at your choice if that's something you choose to do. So that's my understanding of those changes. Anybody have any questions on that or comments? Okay. One of the things on my list, it has like an exclamation point by it, is I need to give you an updated schedule. So, because what sections are we covering when? Is there stuff we're skipping? Stuff like that. So I'm going to work on that. I will say, I think I alluded to this last time, we're going to skip 16.6. So we will not be covering that. So the next videos that you'll be assigned will be from chapter 17. 17.1 is going to be like the only section we're going to have the single video. It's like actually kind of short. The rest of them after that, it's not going to be good. Like 3 video sections, like the rest of the semester, 2 or 3. So that's the plan. Is we're definitely going to skip 16.6, but I want you to not be living day to day like we are right now. And I would like you to kind of know, okay, here's the plan for every week. We only have like 3 weeks left after this. So there's not much time left, or 4 weeks if you count finals week. But yeah, time is upon us, so we need to get that. So that's one of my things I would like to do, is get you a schedule so you know what to expect for the rest of the semester. Today, we are going to go over questions from 16.3 and 16.4. I did not make any extra examples from 16.5. We can do that if you don't have any homework questions. And so that's fine. I think we did all the 16.4 examples already, so I think we're kind of caught up with that. But we'll take some homework questions, and then if there is additional time, we could do some 16.5 examples as well. And then you have that homework is due tonight. 16.3 and 16.4 is due tonight. And to preemptively answer your question, no, I have still not looked at your homework from last week, sorry. All right, let me open up the homework, get that up here. So who would like to get us started and ask some homework questions from 16? Let's do, so I only have to open one at a time. Let's do 16.3. Any questions from 16.3? It's quiet today. Okay, any 16.4, any triple integral questions? Okay, Michael is asking about 16.4, number 23. All right, let's take a look here. Just opening the book up right now. It's thinking. Okay, I think I'm, yeah, there it is, okay. It's nice to be able to have the ebook here. Okay. Oh, right, we talked about this one. We mentioned that it would be different, but we did not actually do it. I feel like most of the time we had been integrating Z first, but this one, that would be a bad idea. Let me resize. Why don't want to let me resize it? That's so weird. What? Ah, sorry, technical issues. That's so weird how it's like pasting that and it won't. There we go. Let me resize it diagonally. Okay. So the idea on these for finding the volume is we want to set up a little representative piece, right? A little cube in here. And we want to either add up all in the Z direction first, or all the Y direction, or all in the X direction. And so I think we had talked about this. We're going to want to add them up in the Y direction first, all the way to the edge out here, whatever this edge is out here, all the way down to wherever this left-handed one is. So we're going to go from the orange one to the blue one. We're going, it's not really left to right, but we're going from We're going this direction. So that's what I would do first if I'm finding the volume, is I would integrate y first. And y just goes from that left one, the 2x squared plus 3z squared to the 9 minus x squared. But then we have to figure out, okay, well then what region do I integrate over in terms of x and z? Okay, that's a problem. We've done this before. How am I going to figure out that integration region in x and z that I need to integrate over? Draw traces. Well, maybe. Traces where? Which traces, I guess? XY and XZ plane. I don't actually think that traces in the XZ plane. See, the problem is I really only care about, you can imagine shining a flashlight. You have this is a flashlight, work with me here. Okay, you're shining a flashlight from the right. And what you're really interested in is what is the shadow that this is casting on the XZ plane over here. So I don't really care where the surfaces actually intersect the XZ plane. I care kind of what's below them or to the left of them. So I think what we need is we need to know where they intersect, right? We need to know where they intersect next. So I think that's what we should.
I had a question about this.
Go ahead, Max.
So if those functions were in terms of x and y, so if it was like a z equals, would we have to solve y for each of them and then set those equations equal to each other?
I started to say to nod yes. You would need to solve for y to get the bounds for the integral, right? You need to have, if you're going to integrate y, you need to have to know what they are in y. I don't think you'd need to do that if you want to find out where they intersect.
You don't need to do that. Okay.
No, because what you're essentially doing is you're solving a system of equations. And that system is going to have infinitely many solutions. What you want to know is, tell me about the solutions that satisfy both of these equations. And so you're really just solving a system. Now, usually what we have is well, they're each equal to y, and so we'll just set them equal to each other. But you're really going to get an equation of two variables that is the solution to that system. So you wouldn't have to solve for y. It would depend on the problem about whether that would be a good plan or a bad plan. It kind of depends.
Okay.
Yeah. So for this one, though, we want to find that intersection. And so we do, in fact, want to set them equal to each other. Oh, and this is another one of these that kind of works out nice. Let's see. So we'll add x squared. I guess it works out nice, but not that nice. So you get a circle. I kind of knew that was going to happen. That's why I drew circle as the shadow in the XZ plane. You get a circle radius square root of 3. So that's the region inside of that. That's the region you're going to have to integrate over in terms of x and z. This is interesting. And I'm pausing here because I almost want to use like polar coordinates, but rotated, like polar coordinates, but polar in the XZ plane. If that makes sense. So what I mean is we can do dz dx next. Z, now let me draw the region a little more clearly here. X, Z. It's a circle that will just work with me. That's a circle. Circle radius square root of 3. And this is the equation x squared plus z squared equals 3. So we could add z up first and say z goes from negative square root of 3 minus x squared to positive square root of 3 minus x squared. And then x goes from negative square root of 3 to positive square root of 3. So that's definitely possible. I don't know if I can zoom in there a little bit. So we can integrate z from the bottom half of the circle to the top half of the circle. And then x goes from negative square root of 3 to positive square root of 3. But whenever I see a circle, I'm thinking, I should do polar coordinates. So honestly, I'm tempted to do, okay, the integral of, oh, I don't know if this is going to work though. Yeah, it might not work. Let's do this. Let's do the first step. Let's integrate y and then see what it looks like next. So let's just do this innermost integral. That'll be y from 2x squared plus 3z squared to 9 minus x squared, which will be 9 minus x squared minus 2x squared plus 3z squared, which will be 9 minus 3x squared minus 3z squared, which will be 9 minus 3 times x squared plus z squared. So the reason why I wrote it like that was now my volume becomes a double integral over the region R in the xz plane of 9 minus 3 times x squared plus z squared dA. And again, that's in the xz plane. So what I would do then is, yeah, we're used to it being x and y, but I would just use polar coordinates then. The region's a circle. You have the x squared plus z squared. It's just not going to be x squared plus y squared. You're doing like a rotated polar, where the xz plane is what you're integrating over. They're just letters. In fact, they're all just letters. If you looked at this and you're like, you know what, I don't want to look at it sideways. I'm just going to make it z equals 2x squared plus 3y squared, and z equals 9 minus x squared. Done, sold, fine. It's the same volume. They're just letters. They're totally just letters. I always tell my students that when they're in Calc 2 and you have to rotate it sideways, you're like, you know, they're just letters, right? You can just switch them. Like it's totally, it doesn't matter. So you could do the same thing here too. But so my point is that I would do polar here, even though it's x and z. I would do polar and integrate, call this 9 minus 3r squared, r dr d theta. R goes from 0 to square root of 3, and theta goes from 0 to 2 pi. And I would bet money that if we open up the solutions manual, that's how the authors of the textbook did it too. Or whoever, actually, I don't know if the authors do the solutions manual, usually not. Usually they pay some other people to do that. Because I remember when I was in grad school, I got invited to make a solutions manual for some work in the summer. I ended up not doing it. I had a different job, but that's why sometimes, you probably haven't noticed it, but I've noticed it. Sometimes the methods that are used in a solutions manual are different from the methods that are in the book, because the person doing the solutions manual forgot to use exactly the same methods that the author used. So, but I bet this would be polar coordinates. I bet that's how they did it. So I feel like we kind of glossed over some of the important concepts early. I don't know if this is too small of a font, maybe it is, but I don't know, Michael, you asked about this one. Does that help you at all? Do you want to clarify part of it again or keep going?
Yeah, no, that's like where I got to. I was just confused about using that identity for r squared with the x and the z. So.
Right. So that's totally legal. Totally legal. Mm-hmm.
All right. Yeah. Thank you.
Yeah. No. Good question. Yep. Good question. Any other questions on this one before we move on to another one?
Can we go over the setup for 22?
Sure. Okay, where's my book? There we go. And oops, do my little snip. Oh no, I'm gonna lose that square root. I gotta do it again. Let's try it again. There we go. So weird how that other one pasted in. This one's just fine. Okay. All right, this one, little easier to begin with, at least because it's the top minus the bottom. It's like, you know, our little representative pieces in here, and we're gonna do, that's the worst drawing ever, but we're gonna go Z first. So we'll go from the bottom curve to the top. At least that's how I would do it. The bottom one is already set up for us, square root of x squared plus y squared. The top we'd have to solve. What is that? 8 minus x squared minus y squared. And then, oh, we have to do the intersection again. Did we do this one or it just looks familiar? I can't remember.
It's similar to 21.
That makes sense. Yeah. Let me see here, because I'm like, it looks so similar. But I don't know. Maybe we did 21 last time. Let me see. Yes. Okay, I'm not crazy. Thank you, Rudy. I mean, I might be crazy, but not, that is not evidence for my craziness. Okay. We need to find where they intersect again, right? So always we have to figure out, because we need to know what's the region below here in the XY plane that we're integrating over. So this is kind of to Max's point about, you know, do I need to solve for this or that? What you're technically doing is you're solving this system of equations. So just to be entertaining here and kind of show you some alternatives, I'm going to do this and solve this system, not by solving for Z. So what I'm going to do instead is square both sides of the second one. I'm going to subtract the x squared and y squared and get them on the same side of the second one. Now you might say I'd add them together to eliminate the x's and y's, but I want to know what's true about the x and y. So I'm actually going to subtract the two equations. That gives me 2x squared plus 2y squared equals 8, which gives me x squared plus y squared equals 4. And that's, so the region inside of that then is my region I'm integrating over. So you could just as easily solve the first equation for z and set them equal to each other, and you'll get exactly the same thing. So that's cool. Okay, so that's the region. Let me do a little sketch of that here. There's where they intersect, and the region we're integrating over is inside of it. This is in the xy plane, circle radius 2. Kind of alludes to polar again. It's kind of interesting here that, I don't know if you've watched the 16.5 videos yet, but that's the cylindrical and spherical coordinates. And on a problem like this, you're kind of already doing cylindrical coordinates because you're doing dz, yes, but I would do polar for the rest. You know, you're going to do the dA and then a double integral over the region R in the plane. But I would not do the dA as dx dy, because then you have to integrate from the bottom half of the circle to the top half of the circle. And then x goes from -2 to 2. I would instead write this as, oh, that just becomes r, the square root of 8 minus r squared dz, and then r dr d theta, instead of the dx dy, and then go from 0 to 2 and 0 to 2 pi. That'll be a much better integral than trying to do the rectangular coordinates there. That's going to be a lot easier. Oh, in fact, oh, Oh, that would be just gross if you tried to do that. Because if you did this dz, when you integrate it, you're going to have square root of 8 minus x squared minus y squared minus the square root of x squared plus y squared. And then you're going to have to integrate that dy. No, no, that's like a couple of trig subs, right? Oh, no, 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 no. So whenever you start seeing circles, you should be thinking, I want to say cylindrical, but technically it's just really focusing on polar coordinates, a 2D polar coordinates. You know, it's a triple integral, yes, but the inside is kind of its own integral, and then you're left with a double integral, and you can choose, do I want to do that double integral in rectangular or polar? And this one is definitely better to do that double integral in polar. So was that enough to get you going, Ty?
Yeah, that helps out a lot.
Cool, cool, cool. All right, good, good, good. What else? Other homework questions?
If no one else has any on 16.4, I have a couple on 16.5.
All right, let me open that up. Feel free to type in the chat if you have some more. I'm going to open 16.5 here. All right, let me get down there. So get us started. Rudy, what were you thinking? Which ones were you looking at, Rudy? Uh-oh, we lost Rudy.
Sorry, had trouble with my.
It's okay. Yeah, maybe just type. Looks like connection maybe is getting a little funky. It happens. Did I tell you that some of my colleagues are requiring attendance at their classes, like literally taking attendance? Did I tell you that? And like giving 2-hour windows for tests. I don't know if I told you this too. Like, you know, I mean, like some of you have other people at home and siblings that need the computer, and you, I don't know how many computers you have, and I don't know. It just seems wild. Okay. Oh, geez, just starting us off easy here. Oh my gosh. Okay, but we should look at the instructions here too. What did it say? In cylindrical coordinates. Oh, okay. So it's giving it to us in rectangular. I was going to say I do not want to do that in rectangular, but then it's saying evaluate it in cylindrical. Okay. Ooh, still, man. So the first thing I want to do here is figure out what is my region? What am I integrating over? So let's keep in mind here, these bounds are y. So x goes from, or y goes from x to square root of 1 minus x squared. And then next one is x, and the next one is z. So this seems like a cylinder to me because the x and z are constants, that they're just fixed bounds there. So I think, I don't know if I can draw this, but yeah, this is not going to go well. I need the 3D version of y equals x and y equals square root of 1 minus x squared. So what are those? That's a plane. This was a mistake to try to draw this, but now I'm into it and I can't go back. So y equals x is a plane, and then z is free. So you know the line y equal x is at 45 degrees in the xy plane here. This is like a bad angle. So let's say this is 45 degrees here. So there's the line y equal x, but we have to make it into a plane, right? It's a 3-dimensional plane because z is free. So it's this plane at an angle of 45 degrees between the x and y axes. And then you have y is equal to square root of 1 minus x squared. In 2 dimensions, that's a semicircle, right? -1, -1, 1, 1. It's a semicircle in 2D, but we are in 3D, so Z is unrestricted. So it's something like that. It's a cylinder. Does that look like anything at all? I can see it in my head. I know what I meant to draw. I don't know if you can see it, but what I see is, let's see. And then we have to look at the bounds, I guess. X goes from 0 to square root of 2 over 2. X goes from 0 to square root. What? 0 to square root of 2 over 2. Square root of 2 over 2 is out here. And then Z goes from 0 to 4. Oh, square root, I was thinking square root of 2. Square root of 2 over 2 is in here. Ah, I see. So that's right where this plane intersects. Yeah, so I think what we have is we have the plane, and then we have the semicircle coming around, and so we're finding the volume of this little wedge. We're finding the volume. Let me switch colors here. You can't read this drawing at all. It's okay. Oh, and it's not even the wedge either, because it's a straight line here. Oh no. X is there. Y goes from, nope, not yet. Not right. That was the wrong bounds. Y goes from the plane to the semicircle. Yeah, that's the wedge right there. So Y goes from the plane to the semicircle, which is a cylinder here. So it's the y-axis, kind of parallel to the y-axis, parallel to the z-axis, and then curving out until you hit the plane y equals x. And then you have up here, you have z equals 4, z equals 1. And then I think that x going from 0 to square root of 2 over 2 is going to be redundant, because I believe that's where they intersect. So I think if we took this point over to the x-axis, that would be at square root of 2 over 2, I think. We'll see. We could check that. Let's go ahead and check that. Let's see, that would be where y equals x intersects with y equals square root of 1 minus x squared. So that would be when x equals the square root of 1 minus x squared. Yeah, this is going to be good. Square both sides, x squared equals 1 minus x squared. 2x squared is equal to 1. X squared equals 1/2, and so x is plus or minus square root of 1, or 1 over square root of 2, which is square root of 2 over 2. And I feel like, I mean, I'm drinking this hot coffee, but I feel like I need to take my sweatshirt off after that. I was like, whew, I was not messing around at all. The reason why I want to do this is because it asks me to do the integral in cylindrical coordinates. If it just said find the integral, I could go ahead and try to integrate it. Now, good luck with that. Trying to find the integral of e to, this is just like a constant, c minus y squared dy. Good luck with that. It is actually not possible. So, but you could try to do that integral, but it didn't say that. It said find the integral into cylindrical coordinates. So we're going to have to do a conversion. And for me, I can't do a conversion just by messing around with bounds. I need to see what is the region that I'm integrating over. So for me, the function here is irrelevant. I focused on the bounds to try to draw the region, to try to figure out what was happening with that region. And that's where I got this little slice of cheese here, or a little wedge here. So I think the rest of it will be pretty easy. I think this was really hard. And so we'll do the rest of it, but let's pause right now. What questions do you have about how we figured out that region?
I don't know if this relates to how we found the region, but I'm trying to wrap my head around the integrand, the function. How does that relate to
What
the
it is,
bounds?
yeah, it doesn't at all. What it is
Okay.
there's some function that varies throughout space, and you can think of it being temperature. And it depends on, well, it really depends only on x and y, but it could depend on z. It's some function of x, y, and z. Yeah, or there's actually, this is what 16.6 talks about, the mass. The mass density, so the mass of an object, the density of the object could depend on where you are. And so what we could be doing is we could say, maybe this e to the negative x squared minus y squared, maybe that represents the mass density, mass per cubic centimeter. And so if we integrate that mass density over the volume, we would get the total mass. And so what this is saying is that the mass depends on where you are. Actually, it only depends on where you are in the xy. It doesn't depend on z. And so it's some function. It doesn't matter what that function is. It changes the answer to the integral, of course, but it has no relation to the bounds at all, zero. It doesn't matter. It doesn't change what you're integrating. Like, think of a double integral. You have some region in the plane that you're integrating over, and then there's some function above it. But what the function is doesn't change the bounds of your integral, which only depend on the region in the xy plane. So this is a 3D version of that. There's some function that we can't draw because it's like a fourth dimension, and it depends on where you are in space. And that function changes where you are in space, but it doesn't affect the bounds of the integral. Is that okay?
Yeah, that explains better.
Okay, good. Any other questions on how we figured out the region so far? Okay, let's see if we can set up this integral now. I need to go down below. And it's not volume. It's not volume now. It's just an integral. You're integrating some function. So the integral, oh, I just did that again. We're going to do a triple integral. We'll do this triple integral over the region D. We use region R in 2 dimensions and a region D in 3 dimensions of this e to the negative x squared minus y squared dv. Okay, so now let's take a look at this. I don't think we need that much space. It said cylindrical. So we need z, and then r, and then theta. So z just goes from 0 to 4 of e to the negative x squared minus y squared dz. That's fine. Z goes from 0 to 4. Then we have r dr d theta. So I guess we need to look at that little pi in the xy plane. Because that's the region that we're integrating over in the xy plane. Any thoughts on r or theta or both?
Wait, so you wrote dz as the innermost integral, right?
Mm-hmm.
How they set it up was that their innermost integral was y and then x and then z. Are we just changing that for just how easy it's going to be, or?
what we're doing is we're changing it because they did it in rectangular coordinates, and then we want cylindrical coordinates. So in cylindrical, you're going to do DZ. You don't have to do DZ first, but usually you do DZ first.
Okay.
Yeah, so it's because of the change in coordinate system. Rudy's nailed the theta. You are correct. Pi over 4. Remember, this is the line y equal x. And so that means theta starts at pi over 4 and then ends up at pi over 2. So you are correct. Pi over 4 to pi over 2 for theta. Excellent. And then we just need r. We need r as well. I'll give you half of it. Starts at 0. You got to kind of go back to where that outer surface came from. Zero to 1. Michael's got it there. Yep. Michael Giannopoulos has got it. 0 to 1. R goes from 0 to 1. It's the circle. It's a cylinder. Y equals square root of 1 minus x squared extended up and down. But in the xy plane, it's just the circle. Y equals a semicircle. Y equals square root of 1 minus x squared. And so indeed it would be 0 to 1. We have one other problem. I know we've talked about this before. This is not going to work what we have written right here. So what's the one other thing we have to fix?
The integrand itself.
Yep. If we're going to be in cylindrical coordinates, we can't be integrating over x's and y's. So let's fix that. 0 to 4. This would be e to the negative r squared, right? X squared plus y squared is r squared if we factor out a negative. And then it actually becomes a doable integral because of the extra r you have there. The e to the negative x squared minus y squared trying to integrate that dy is actually not possible by hand. You could type the integral in a calculator. It could do it for you. I don't know if your calculators could actually, but you could do it in a powerful actual computer integral calculator. But by hand you can't. But this one you can. It's just going to be a simple u sub once you get to the dr. The dz is easy because there are no z's here. So it's just e to the negative r squared. I'm going to toss the r in there with it. Then it's z from 0 to 4 dr d theta. So pi over 4 to pi over 2, integral from 0 to 1, and then you just get 4r e to the negative r squared dr d theta. It should be easy from there. All right, I think this was Rudy had asked about this one. How does that feel right now? Is that okay? Okay, excellent. And then you said you may have had a couple. Do you have another one too? All right, 29 is a second one. Let's see here, 29, mass from density, volumes and cylindrical. Okay, another volume one. All right. Find the volume of the solid bounded by the plane z equals 0 and the hyperboloid z equals 3 minus the square root of 1 plus x squared plus y squared. Okay, so there actually is there's a top half to this hyperboloid. There's another one up here, but we don't care about that one because we're only looking at between it and the xy plane. By the way, I know that because of the extra 3, so it just like the center of it got shifted up 3. That's kind of what happens there. But we only care about this portion of it. Boy, we don't even need, this doesn't even need to be a triple integral. Did it tell us we have to do a triple integral? Use, oh, those jerks. That's okay. So it does say use cylindrical coordinates. Really, we could do it just with polar coordinates, but we can do cylindrical coordinates. That's fine. The volume will be the triple integral over the region dv. And for our dv, is we're going to have to do dz r dr d theta. I don't know, does the book put the r in front of the dz? It doesn't matter, but I like putting it this way because it kind of ties it into the polar in 2D. So, all right. Okay, well, z, we got a little cube in here. Goes from 0 up to the surface. So 0 up to 3 minus the square root of 1 plus x squared plus y squared. And then we just need to figure out the integration region in 2D. Looks to be circular. How do I find the equation for what appears to be a circle? How do I find the equation for that circle?
You set the hyperboloid equation equal to 0.
Equal to 0, right? Yep, here we're finding a trace. We're finding a trace here. Yep, you got it, Michael, or Rudy as well. So 3 minus square root of 1 plus x squared plus y squared equals 0. So 3 equals square root of 1 plus x squared plus y squared. I always make these, well, this one doesn't work out quite as nice. I was thinking it would, but no. We're going to square both sides and get 9 equals square root of 1 plus x squared plus y squared. And, oops, we squared both sides, sorry. And so we get 8 equals x squared plus y squared. All right, so that's a circle radius square root of 8. Okay, I think we're all right. So, oh boy, we're good. Oops, sorry. R goes from 0 out to the edge here. So that would be 0 to square root of 8. And yeah, you can write that differently if you like. 2 square root of 2. That's fine. And then theta goes all the way around. 0 to 2 pi. And I feel like this happens on all of these. We got to make sure we're in terms of cylindrical coordinates. So we've got x's and y's in here. That's no good. So 0 to 2 pi, integral from 0 to square root of 8. And then integral from 0 to 3 minus the square root of 1 plus r squared dz r dr d theta. So that's the setup. Just looking down here, I have a to-do list. This is awesome. That was like last week's to-do list. I'm finally done, except for your homework. Sorry. But I'm going to throw that one. I started a new list and your homework just got copied over to the new one. Okay. All right. Are we good so far, Rudy, on the setup? Or anyone else? Any questions so far on the setup? Okay. Okay. All right. So now let's see if we can keep going. That's good. Integral 0 to 2 pi, integral 0 to square root of 8. This will be z from 0 to 3 minus square root of 1 plus r squared, r dr d theta. Uh, 3 minus square root of 1 plus r squared, I guess minus 0, so we don't need that, and then r dr d theta. I feel like we've done one like this. I was going to suggest, oh, we should distribute the R and split it up into two separate integrals, but I don't think that's necessary, and I think it almost unnecessarily complicates our work. I think we can do a U sub right now. I think we should be good. Let's do that. U equals square root of 1 plus R squared. Oh, no. U equals 1 plus R squared. That's what I meant. Du is 2R dr, so 1/2 du is R dr. And then u at 0 will be 1 plus 0, that's 1. And then u at square root of 8 is equal to 9. Nice. No. Yeah, right, square root of, yeah, so square root of 8 squared is 8. And then plus 1 is 9. Okay. I think that's good. 0 to 2 pi. Ooh, we have a 1/2 integral from 1 to 9 of 3 minus square root of u du d theta. I feel like these steps are the ones where, like, you know, having taught calculus quite a few times in recent years, I start to go like really fast, and that's not always good because there's a lot of fine details. Does anybody have any questions about the transition there from R's to U's? Okay, I am not seeing any. Let's go ahead and integrate. Integral of 3 will be 3u, and then integral square root of u would be u to the 3/2, then times 2/3 from 1 to 9. That's all d theta. Let's see, 3 times 9 minus 2/3 times 9 to the 3/2 minus 3 times 1 minus 2/3 times 1 to the 3/2. And that's all d theta. Oh boy. 27 minus, let's see, 9 to the 3/2. Square root of 9 is 3. 3 cubed is 27, but then we're dividing by 3. So that's 9 times 2 is 18. I feel like it's one of these, like, don't try this at home. Like, don't try to do all this in your head, but and then the 1 to the 3/2 is just 1. Oops, sorry, whoa, slow down. Three is 9/3, so that's 7/3. And we have 27 minus 18 is 9. That's 27/3 minus 7/3, so 20/3. D theta. Think. And I guess we're almost done. 10/3 theta from 0 to 2 pi. And so we would get 20 pi over 3. Any questions on finishing up that integral there? Lots of arithmetic there. Okay, good. Did you get through the part where you got stuck, Rudy? That's the worst, where you're like, I had all the work and I ended up with with 20 thirds instead of, or whatever. Yeah, 20 thirds instead of, or 40 thirds instead of 20 thirds. That's the worst. Then you can't find out where you went wrong. And it's funny how the brain will have this like neural pathway where there's like a neuron, and then it's connected to another neuron, it's connected to another neuron. And if it should have gone this way and it went this way instead, when you look at the problem again, you're going to keep going the wrong way if you keep looking at it, because it's like train. You almost have to like put it away and start all the way over. But your brain is like, I don't want to start all the way over. So it's tough to find those small errors like that. You just look at it and don't see it. Cool. All right. We're still taking questions. I do not have any 16.5 examples, but we have about 10 minutes left. I could certainly, we could just pull one up here if there are no additional questions. Anybody have any other requests from 16.5? Homework list out here.
I don't really have a specific question in mind or like a number in mind, but I'm having trouble understanding the bounds of spherical coordinates.
Yeah, those are not, yeah. So let's do one here. By the way, a lot of times they make them easy when it's like the unit ball. So let me pull one of those. Those are the easiest ones. And then we'll do some that are more interesting, and we'll do one that's a little harder than that. But let's do this one. Let's just see if we can set up the integral and set it up in spherical coordinates. The keys for spherical: x squared plus y squared plus z squared is equal to rho squared. And when you have your point out here, which is x, y, z, just so you can visualize it, rho is the positive distance from the origin. If you project this down to the xy axis, xy plane, I should say, theta is still the angle from the positive x-axis. And then phi, because everybody needs another Greek symbol, phi is the angle from the positive z-axis. So rho is the distance from the origin out to the point. Theta is the angle from the positive axis to like the shadow of it. And then phi is the angle from the positive z-axis down to your point. So this one, the unit ball is simply a ball, radius 1 unit, centered at the origin. So we have x squared plus y squared plus z squared to the 5/2 looks like a terrible integral, but x squared plus y squared plus z squared is rho squared. And then you have dv is rho squared sine, moment of panic here, sine phi d rho d theta. So like, I haven't done one of these in a while. Like, wait, double check. It was like a week ago when I made that video. Let's see here. There's cylindrical. Okay. Whew. I am not forgetting everything. That's good. And then we just need to figure out our bounds. I guess I did them as phi first. So since we're doing the whole sphere, we're going to loop all the way from the positive z-axis to the negative z-axis. We're going to have rho going from 0 to 1. So you have to think of, let me draw another one here, x, y, z. Rho is going to be 1. We're going to rotate all the way from the positive z-axis to the negative z-axis. So phi is going to go all the way from 0 to pi. Rho is going to go all the way from 0 to 1, all the way around here, all the way from 0 to 1. It's the unit ball, so the radius is 1, 0 to 1. And then theta is going to go all the way around. We're going to rotate all the way around to get this ball when we're done. So theta is going to go from 0 to 2 pi. So the rho squared sine phi d rho d theta, that's just dv in spherical coordinates. The derivation for that was in the video, but dv in spherical coordinates is just always that. X squared plus y squared plus z squared is rho squared. And then again, the volume, the region that we're integrating over is the unit ball. So we integrate from 0 to pi, from 0 to 1, and then all the way around 0 to 2 pi. And that's actually not a difficult integral to do. It's just harder to set up, because you end up with just a polynomial in rho. Because it's just rho, it'll be rho to the 7th, because you got rho to the 5th here times rho squared. And then sine phi, your inclination might be, some of these you might look at them and like, oh, I'm going to have to do parts because I have a constant, have a function times sine. But no, it's one's a rho and the other one's a phi, so they're just integrate them separately. So
Wait, so why are we doing it? Why are we integrating with respect to phi first?
you don't have to.
So you could still do like d rho, d phi, d theta. Doesn't matter. Okay.
Nope. Especially, see, this is like, do you remember the ones in 2D when we started in 16.1 integrating over a rectangle? And since we're integrating over a rectangle, we could just pick x or y first. It's constant. If we're integrating over some other region, then we have to be really careful. We have to, am I doing y first and then x, or am I doing x first and then y? We have to be really careful. And that was in 16.2. Well, in spherical coordinates, the unit ball is like a rectangle. And so you could integrate whatever order you want. It's going to be fine. You don't have to think very carefully about, well, I have to do the rows first out to this because that row depends on phi or something. But here it's constant. It's always 0 to 1. The phi is always 0 to pi, no matter what rho is and no matter what theta is. So in this particular example, the order is not going to matter, and you can just switch them around whatever order you want to do first. But that will not always be the case. I will say, you remember polar coordinates and cylindrical coordinates? When do you use those? When you have polar or cylindrical?
When there's a spherical type shape.
Right. Right, in the XY plane, or yeah, your region is a circle. So you're only going to use spherical coordinates when your region is a sphere. Like, honestly, like that's really the only time you're going to use spherical coordinates. And this will come up later on in the course when we get to some really interesting stuff that we're integrating over a sphere. We're only going to use spherical coordinates if the region we're integrating over is a sphere. But in theory, there are other regions too, but that's really the only one we're going to use it with. So that's the first one, Max. That one's not super interesting, but that's that first one. Does that help at least with that setup there for that one?
Yeah. With cylindrical, it's a lot easier because we're used to dealing with like trigonometry and stuff. But with like a whole phi thing in the row, it's a new concept that a little hard to understand first.
For sure. Let's do another one. I think we have time for one more setup. So let's do another spherical one. But these already have it set up for you. So that's not as interesting as the ones, because your challenge was like setup, correct?
Yeah.
Yeah. Oh, okay. I don't want these to be too crazy. I don't know. Well, let's try 49. This might be a mistake. I have to go in like 10 minutes. So I have a really important video conference. My kids are getting together with their friends to do a Lego building contest. Super important. Crucial Zoom meeting. Priorities, you know. Okay, so sphere and the hemisphere. Okay, so the blue part is the hemisphere, rho equals 1, where z is greater than or equal to 0. And then the tan or gold or whatever is the rho equals 2 cosine phi. Michael, to your earlier question, this one is going to matter. The order is going to matter here. So we'll need to think about that a little more carefully. So yeah, I think we want to integrate rho first here, because what we have is we have like a hemisphere on the bottom, and then we have the blue hemisphere on the top. Let's go ahead and draw it. I don't know if you can see, like they're going to intersect right here. And there'll be a blue one on the top. And then like a gold one. Can I like get a gold color? Something like this. Yeah, okay. On the bottom. Right, so you're gonna have the gold on the bottom, the blue on the top. So what I would do is I would integrate rho first. And we have our rho squared sine phi. I would do rho first, and rho goes from the gold to cosine phi to the blue 1. I want to like check the answer before I let you go here. I think phi is the next interesting one. Phi will go from the positive z-axis just to pi over 2, I think. Right? We don't want to go past that. So I think phi would go from 0 to pi over 2. And then theta, we do want to go all the way around. So phi, what I mean by that is if you have your representative piece in here, you have the rho going from the gold one out to the blue one, and phi is the angle from the positive z-axis. So phi starts at 0 when it's at the positive z-axis, and you're going to go all the way down to, like, it's going to get smaller and smaller and smaller because you're following the gold. But you don't want to go, like, phi is going to be at most pi over 2. You go below that and there's nothing there. So I think it's just 0 to pi over 2 on this one. And then d theta, we do want to go all the way around for theta. That would be 0 to 2 pi.
I'm confused on the order of the bounds for rho. Like, why does it go from 2 cosine phi to 1?
Does it feel like it should be the other way around?
Yeah, like
Yeah.
just to me, just because of the picture.
I know, it is confusing. So let's draw the two separately. So the blue one, you have your XY plane, and then there's the blue one. Right. And so that one is a hemisphere radius 1. Then you have the gold one. Hold on.
It's 305.
Uh-huh.
Okay.
He's anxious to get started with the Lego contest. The gold one is another sphere radius 1 actually, but it's centered up at 1. So the bottom of that one is at the origin. And so if you overlap them, the origin, the tan one is actually the bottom one. See, if you overlap them, that gold one is actually the bottom one and the blue one is the top one. So rho goes from 0 or from the gold one. Oh, actually, you know, oh, this might be worse than I think it is.
It's confusing me because they're both at the origin.
Correct. I think I need to think about this a little bit more. This is the problem with not looking at these ahead of time, because I think rho doesn't rho always starts at 0, and then it goes out, and then the question is, what does it go out to? Yeah, this is not correct. This is definitely not correct. So if you look at, because we did one like this before that had a hemisphere, and if you're doing rho going from 0 out to 1, that's this, that's just the blue, but then the other one is coming around it like this. So I think you actually need 2 separate integrals for this one. Sorry, I don't think this was a good example to try to do in the last minute. Yeah,
So,
I think,
like,
go ahead.
so you think like the first one would be like 0 to 2 cosine phi, and then like the other one would be like 0 to 1.
Correct. And then what would change about the 2 integrals? Because there has to be something different about them.
Phi.
Phi, correct.
So like
Phi.
one of them would go to like pi halves or something, or pi over 4.
Yeah, I'm guessing that this is, if we find the intersection of those, this is probably at pi over 4 is where the 2 intersect. Yeah, so I agree. So I think it would be, there'd be 2 of them here. One would be, this is not fair because I can just erase a lot easier than you can. 0 to 1, when phi is from 0 to pi over 4. And then from pi over 4 to pi over 2, it's 0 to 2 cosine phi rho squared sine phi d rho d phi d theta. Yeah, I think looking at it for me, I'm glad you brought that up, Michael. For me, looking at it from the side was a better idea. Let me kind of draw this here. So kind of see the colors again. So the tan is the bottom, and for those, R is going from 0 out to rho equals 2 cosine phi. Both of them start at 0 though. Regardless of where you are, here, rho starts from 0 and goes to 1. From here, it starts from 0 and goes out to the 2 cosine phi. Yep. That is better. Cool. All right. I have held you late. I have some other stuff to get to here. I just want to log off with quick, see if I can just double check and confirm. I want to send you, to make sure I send you off here with the right thing. And let's just double check because we do have the answers. And a reminder here, you have 16.3 and 16.4 due tonight. And then 16.5 you should be working on over the weekend. And then I'm going to record 17.1 and 17.2 videos for you. I'm also going to post an updated schedule. So you will have the schedule and kind of know what to expect as we progress here. So we're not just kind of winging it week by week. That will help. That will hopefully help. But before we log out here, which this was 16.4, number 49. No, 16, I was going to say that's not a spherical integral. 16.5, number 49. Oh, yeah, it's close. Yeah, not quite. Not quite. We need to look at this again. So we guessed it was pi over 4. But it's not pi over 4, it's pi over 3. That's when the 2 cosine phi is equal to 1. So it should be pi over 3. They did it a little bit differently than I did. It's not obvious why. I'm looking at their reasoning here, and I don't think their reasoning is super obvious to a student. So we should have been a little more careful and figured out where they intersect. When does 2 cosine phi equal 1, that's when cosine phi equals 1/2. And that is when phi is equal to pi over 3 or pi over 6? I can't think right now. It's pi over 6, right? No, that was square root of 3 over 2. Yeah. Whew, pi over 3. So our picture is a little bit off. It's not pi over 4. It's actually pi over 3. We had the right idea, though. Okay, I have to cut you off there. I'm sorry. I'm going to leave it there, and I will post this replay in case you want to watch through some of this again. If you see any other mistakes here, feel free to let me know. Comment on the video maybe so other people see it, or let me know and I can comment there. Also, I would love to see more questions in the Discord chat. It's been pretty quiet there, and I think that's a good resource. You know, I'm on there and I check it too, but sometimes your classmates might see it. Just use your phone, take a quick snapshot, post it. You know, here's what I'm working on. I think right now, especially for the rest of the semester, that's a really good place for you to help each other too, and kind of help us get through this if you get stuck. Okay, I got to run. Got some Legos to work on. See you, everybody. Work hard this weekend. Homework due tonight, and I will see you next week.